All right, let's talk through Unit 1 in-class review. So we start with number 1. Kim goes for a run in a perfect square that has the same 5 kilograms sides on all 4 sides. We got 5, 5, 5, and then another 5. All right, so we'll say that they start right there in the corner, and she stops exactly in the same spot that she started. Okay, so that means that both of those are the same spot. So anytime we look at displacement, you go around the circle, you come back to the same spot, that's going to be 0 kilometers. What distance did she run? That's a 5, right? That's a 10, that's a 15, and that's a 20. Oops, sorry. 10, 15, 20. So this should be 20 kilometers. All right. How far does a train travel in an hour and a half if it travels at 42 meters per second? All right. So our time here is 1.5 hours. Our looks like velocity there is going to be 42.0 meters per second. All right. Because that's in meters per second and because that's an hour and a half, we got to convert that. So there's 3,600 seconds in 1 hour. All right, so what that means is, if I get my calculator out here, 1.5 times 3,600 is going to give me 5,400 seconds. All right, so we're going to use V equals delta D over T. All right, it doesn't say that that time is changing, so that's likely our av. So 42 equals our delta D over 5,400 seconds, okay? Put that over 1, I'm going to cross multiply. So 5,400 times 42 should give us a delta D of 226,800. And that's going to be meters. All right, a rocket is launched from rest, so VI equals 0 meters per second, and accelerates for a displacement of 46,000. So my delta D equals 46,200 meters. If it takes the rocket 425 seconds to travel this far, all right, what is its average velocity? Okay, so what we're going to do is we want to find average velocity. Well, we don't necessarily have to worry about it being at rest because remember, VAV equals delta D over T. All right, so with VAV being delta D over T, okay, the initial velocity is nice, but it doesn't necessarily help us there. So we know that it goes 46,200 meters, and it does that in 425 seconds. All right, so 46,200 divided by 425. What we end up seeing is that the average velocity is 108.71 meters per second. All right. Jason, the jet pilot, accelerates his plane from rest. So VI equals 0 meters per second at a rate of 62 meters per second. Okay, so that's going to be an acceleration, 62.0 meters per second squared. For 10 seconds, that's a time, 10.0 seconds. Okay, what is the velocity of Jason and his jet at the end? So we're looking for VF. All right, so then we'll use A equals VF minus VI over T. 62 equals VF minus 0 over our time of 10 seconds. All right, ratio that up, multiply those two together, divide by 1 over there. My VF here should be 620 meters per second. All right. Megan is driving her car at 15 meters per second when she slows down to 5 meters per second in 7.5 seconds. What's her average acceleration? So if she starts at 15 meters per second, she ends up at 5 meters per second, and the time it took was 7.5 seconds. All right, we want A equal here. All right, let us do A equals VF minus VI over T. So that's going to be A equals my final, which is 15. Oops, sorry, no, not 15. My final, which is 5, minus my 15 over my time, which is 7.5. Okay, so that's going to be 5 minus 15, which is 10, or negative 10, sorry. So 10 divided by 7.5. And we see that the acceleration here is going to be negative 1.33 meters per second squared. Negative helps because that tells us we're actually slowing down, which is what she's doing. Peter the Panda is running after Dr. Doofenshmirtz. Peter the Panda runs at 12.5 meters to chase down Doofenshmirtz. It takes him a full 3 minutes to catch him because he has a head start. How far, so that's distance, did Peter the Panda have to run to catch him? All right, so our av here, because it doesn't say anything different, 12.5 meters per second. Our time here is 3 minutes. I already can see the problem there. All right, times 60 seconds in 1 minute. So that's going to be 180 seconds is how long it takes. How far? That's going to be delta D is what we're trying to find there. All right. So VAV equals delta D over T. So this will be 12.5 equals delta D over 180. All right. Put it over like that. Cross multiply. Divide. 180 times 12.5. My distance here would be 2,250 meters. All right. Convert the following. A young lad is taking a trip. He was told that the boat would cover 3,785 nautical miles. 1 mile is equal to 0.869 nautical miles. How many miles would the trip be? All right, so if I've got 3,785 nautical miles, and that's over my unknown miles, that's going to be equal to 0. Let me move that up. 0.869 nautical over 1 mile. All right, cross multiply and divide. So my unknown will be equal to 3785 times 1 divided by 0.869. So this should be 3785 divided by 0.869 should be 4355.6 miles. All right. If you have movie pitch and rated scripts where the Oreos don't exist, 2.5 decades is in the future. How many days does that certain teacher have to stockpile before it comes to reality? Okay, 1 day or 1 decade is 3,650 days. Boy, that seems awful short. I think it should be probably 36,000, but we're going to treat it like it's true. All right, so if we got 2.5 decades, all right, and we want to know how many days that is, that'll equal 1 decade over 3650 days. Still think that's wrong, but okay, whatever. Times, divide. So our question mark here is going to equal 2.5 times 3650 divided by 1. So 2.5 times 3650. Yeah, there's no way that's right. That's like in 2 years. 9,125 days. Yep, it's probably 90,000 days in all honesty, folks. So, as little as 7 milliamps can kill a person. How many amps would this be? All right, so we got KHD base DCM. Starting at the milli, 1, 2, 3 to the left. So if I've got a 7, 1, 2, 3 to the left. So that's going to be zeros. So this should be 0.007 amps. All right. Draw graphs for the following scenarios. You've just gotten to the bottom of the hill on Dot, and you are coasting on your unicycle while trying not to fall. As you reach Lake Marion Elementary, you come to a complete stop. What does the distance versus time graph look like? Okay, so if we come to a complete stop, that means that we have to be slowing down as we go that way. All right, so we're gonna take this thing and then make it nice and flat at the end. So that's going the positive direction, slowing down, and eventually, because it goes horizontal, it stops. You decide to try your basketball shooting skills, except doing so with your feet on the ground is boring. You get to the highest part of your roof and you shoot from there. What does the distance versus time graph look like for the basketball? Okay, well, it's going down, so down equals negative, right? And the reason why down equals negative is because on that y-axis, right, up is positive, down is negative. So if it's going down, it's going in a negative direction, all right? Now, it should go faster down too, so it's gonna speed up downwards because gravity's gonna pull on it. So if it's going down, right, and then it's gonna speed up as it goes down, so then we should see that thing start to spike as it goes faster and faster downward, okay? A student once decided to stand defiantly in the back of the room. They stood there for what seemed like days without moving. It turned out to be a holographic image sent forward in time by the same physics teacher, but when he was a high school student. Weird. What would the distance versus time graph? If he's not moving, that's gonna be a nice straight line like that, all right? Because the distance doesn't change over time, so it just stays the same. All right, let me know if you got questions.